Good morning, everyone. Welcome back to our tutorial on standpoint logic. So in the previous two sessions, you have seen propositional standpoint logic along with a proof theory, a proof system for actually showing things in this logic. And you have seen later on first-order standpoint logic, where you had the same outer logic, so to speak. You had standpoints, and then these standpoints have precisifications, but in contrast to propositional logic, in these precisifications you don't have propositional valuations, but you have first-order structures. Right? And this you can, of course, also do with other logics. Right? So what you put into the precisifications is up to you. And today we are going to look at some other options, what we could potentially put there. So Tim has already hinted at us starting with looking at standpoint description logics. And to do this, we will first of all recall plain description logics with their syntax and semantics. And then we will look at a number of standpoint description logics. And as usual, our goal will be to find fragments of logics that we can extend by standpoint modalities without affecting the computational complexity of their reasoning problems. Right? So this is not a given. This does not follow automatically. We will also see fragments where complexity increases. So typically we have to do some work to keep complexity under control. Right? But as you will see, there are several fragments where we can successfully do this. So the first standpoint description logic we're going to look at is this EL language, and then later on we will also look at more expressive standpoint description logics that have fancy names, so I will go into details later. So, but before we dive in, you might be wondering why there are three names here, but only two presenters. So originally, Lucia and Tim proposed to do this course. Then Lucia couldn't make it, and Tim asked me if I would be willing to fill in for her, and I happily do so. Just have to say, so I was involved in the work on some of the standpoint description logics, in particular in the work with EL. The more expressive stuff was work done by Lucia and Sebastian Rudolph. So while I can show it to you, I'm not deeply knowledgeable about the technical constructions. Right? So if you have any more detailed questions, I would refer you to the respective papers. And then finally, probably tomorrow, we will look at a non-monotonic version of standpoint logic, where the focus is a bit different, so where we can do some other stuff. Okay, so before we dive in, any questions on your side, any stuff that might be unclear from the previous 2 days, or any other questions you might have on the things lying ahead? None so far. Okay, so yesterday you have seen first-order standpoint logic. Right? So where basically you have first-order logic, and you can put standpoint modalities anywhere in formulas of first-order logic. You have also seen the so-called sentential fragment, and the idea there was that you can use standpoint modalities within first-order formulas, but only in front of sentences. Right? So this is a formula from the sentential fragment of first-order standpoint logic, because what is after the standpoint modality is a first-order sentence that is a first-order formula without free variables. Right? This fragment is useful because essentially it is well-behaved. Right? So Tim has shown that it still has a small model property, and that means we can essentially compile away the standpoint modalities and reduce this language to the base logic. Right? So this works for propositional logic. It also works for this sentential fragment. And this essentially works because if you only have sentences after these modalities, then these sentences will either be true or false in a structure. And what happens there is therefore essentially propositional. Right? However, on the other hand, it's not really practically useful to have this fragment. Right? So we still have full first-order logic, so the language is still undecidable. So we do not suddenly gain decidability. We have a simpler logic, but also it's less expressive. Right? So that's why we were looking for further fragments where we can actually express things we want to express, so fragments that are more useful, but at the same time also we were trying to go or to restrict the first-order logic that's being used here further in order to move towards decidable languages. Right? And in particular, what we want to do when using standpoint logic for knowledge representation purposes is we want to express bridge axioms. So this is one example of a bridge axiom. And basically what it does, it provides a bridge between different standpoints. Right? So this sentence here says, for all x, it holds that if, according to the land cover perspective, x is unequivocally a forest, then conceivably, according to the land use perspective, x is a forest. Right? So this relates the same term, namely forest, as it is being used from different standpoints, so from different perspectives. But the important point is, syntactically, this is no longer in the sentential fragment. Right? So after the standpoint modality here, you have an atomic formula with a free variable, so this is no longer sentential. But this is required for what we want to do for expressing these bridge axioms. Right? So we want to be able to say something about individuals individually. Right? So we want to speak about a single x and say something about this x and how the land cover and the land use perspective relate for these single instances. Right? So whereas the sentential fragment only speaks about true or false, here we want to speak about properties of single individuals. Right? This is something that we want to express. However, in general, this is not easy to do, right? Because classically, allowing these free variables behind modalities increases complexity. Fortunately, people in modal logics, and in particular people studying many-dimensional modal logics, have identified this problem long ago and have proposed one potential solution. Namely, they said, well, we need not, or we cannot allow an unrestricted number of variables within the scope of modal of modalities. So let's just try to restrict to allowing only one free variable. And this leads to the so-called monodic fragment, and mono because it's only one, right? At most one free variable. So this extends the sentential fragment because if you have no free variable, you have at most one. But you can also express these bridge statements that we had before. Right? So here you have at most one free variable after the modality. Here, the same. Right? So this would be within the monodic fragment, and it already expresses what we want to express. Right? So our next target will be looking at monodic fragments for restricted versions of first-order logics, in particular description logics.
Usually you call this property monodic with an A. Why did we choose to put an O here like monodic?
The monadic refers to the arity of predicates. Right here we are referring to the number of free variables in sentences. Okay, so and also that this is not our choice of name, right? So this is what people in many dimensional modal logics decided to do. So we will therefore start out with this monodic fragment, right? So inspired by work on many dimensional modal logics. And the first order standpoint logic is essentially a many dimensional modal logic, right? So we have one dimension for the standpoints, the other dimension for the interpretations within the precisifications. Right? So, and because using full first order logic would still be undecidable, we are going to well-behaved fragments of first order logic. And as such, description logics are a very natural candidate because they are well studied and also well behaved. And by allowing this one free variable, we can express bridge axioms, and this is going to be one of the most useful things when using standpoint logics in the context of description logics. And we will see that in the cases I present, adding these standpoint modalities to a monodic fragment, typically, and this is in quotes, because this is by no means universal or automatic, right? It typically comes at no extra computational cost, but only because we worked hard for it, right? So you cannot simply add standpoint modalities to your monodic first order logic and then everything is fine. You really have to identify the proper fragments. Sometimes we will also see that adding this or that constructor to the description logic will break tractability. Okay, so this is our aim. So we want to extend description logics by standpoint modalities, but within the monodic fragment, so we can actually express these bridge axioms, which are going to be useful for aligning ontologies with one another. Right? So we can say, if something is a forest according to the land cover ontology, then it relates to how the land use ontology or the land use standpoint sees something as being a forest. Okay, so description logics. So you might have heard of them. Anyway, here's a brief recap on what that is. So there is not a single description logic, but many of those, and they are built by using different constructors. The aim is always to represent knowledge, typically ontologies, but in general, any kind of structured knowledge about a certain application domain that you might have. The starting point is having a vocabulary consisting of these three sets. So you have concepts that correspond to unary predicates. So expressing properties of objects. You have roles, which basically correspond to binary predicates, so relations between individuals. And then you have individual names, and they correspond to concrete named individuals. So our restriction of first order logic that we do here already starts at the syntactical level, already at the level of the vocabulary, because we only allow unary and binary predicates. Right? So in general, first order logic, we would ordinarily have predicates of arbitrary arity. Here we restrict to unary and binary. And then, using this vocabulary, we can build more complex concepts. So sometimes also called concept terms. And how exactly this works depends on the concrete description logic we're using. I will show you some examples later on. This is one of the more expressive description logics shown here. And this is mostly to show you some of the constructors. Right? So C and D are complex concepts, and you can build them using an atomic concept, so something that is a concept name. You also have the top concept, standing for the set of all individuals. Right? So top is the property that holds for every individual. You can have, once you already have two complex concepts, you can conjunctively conjoin them. Right? So that is to be interpreted as the intersection of these two things, or having to satisfy both properties. You have this existential restriction expressing that an individual satisfying this must have an R successor that is a C. You sometimes have negation, so can specify that property C must not be satisfied. You have universal restriction saying that all R successors must be C's. And just like you have a dual of the existential restriction, of course, there also is a dual to this conjunction, namely disjunction. And sometimes, in some description logics, you also have some more expressiveness. So this, for example, is a qualified number restriction saying you have to have at least n R successors that are C's. Right? And so those are some of the expressive means that you have, and by not allowing some of those, or maybe adding some further, you get to different description logics with different expressiveness, with different complexity. And our goal is to look at several of those and see to what description logics we can add standpoint modalities without losing potentially nice computational properties. So when using description logics, you typically split your knowledge base into two parts. You have one terminological box, the so-called T-box, containing general axioms regarding terminology of the domain. Right? Syntactically, they take the form of so-called general concept inclusions, saying that everything that satisfies C must also satisfy D. Right? So every C is a D, basically. And this is called general because you are allowed to write complex concepts according to this syntax on the left and on the right. So previously there were simple concept inclusions where one of those had to be atomic. Nowadays we allow general concept inclusions. There are also complex role inclusions where you can build role chains on the left. So these roles are binary relations, right? And you can chain them, and then you get a new binary relation. Here you can say, if two things are related in this chain, then they must also be related in S, right? And this, so there are also simpler role inclusions where you only are allowed to write one role name on the left and one on the right. But sometimes these more complex role inclusions are also allowed. And the useful thing is that, for example, you can use it to express that a role must be transitive. Right? So if you write R, circle R is subsumed by R, then basically you say anything that you can do in 2 steps, already you can do in 1 step, giving you a transitive role in the end. So that's the terminological box, the T box. And then there's also an A box, and this contains ground facts about your individuals. Right? So whether something is a forest, how it relates to some other piece of land, so knowledge about concrete facts that you have are put into this A box with the A standing for assertions. So that's the assertional knowledge, right? Talking about one concrete instance. Well, this talks more about the domain. So that's the syntax of description logics. The semantics are given by logical interpretations. So just like in first order logic, you have an interpretation domain and an interpretation function. The domain must be some non-empty set. And this interpretation function interprets the vocabulary elements as follows. So concept names are interpreted just like unary predicates would be interpreted, so as subsets of the domain. role names are interpreted as binary predicates, so binary relations on this domain. Individual names are just objects, right? So they are just elements of this interpretation domain. And then, once you have this, once you know how to interpret the vocabulary, you know by structural induction how to interpret these complex concepts that you can build in the syntax. Right? So the top concept, being true for everything, is interpreted as the set of all individuals. Conjunction is interpreted as the intersection of the individual interpretations of the concepts, of the conjunct. Existential restriction is interpreted, so exists in our C is interpreted as the set of all X in the interpretation domain for which there exists a Y that is R related to X, right? Which is an R successor of X and which is a C, right? So which is what this existential restriction is supposed to express. Negation is interpreted as the complement with respect to the whole interpretation domain. Dually to existential restriction, we have this universal or value restriction saying that all RC is interpreted as the set of all X, for which it holds that all R successors Y are Cs. Right? So only has R successors that are Cs. And the number restrictions are, as you would expect, right? So you have an existential restriction where you additionally require a lower bound on the number of such successors. Right? So what you do here is you take the cardinality of the set of all Y that are R successors and Cs, right? R successors of X, and you check that the cardinality of this set is at least n, right? And then you collect all X that satisfy this. So all X that have at least n are successors that are Cs. And whether or not these constructors are allowed in your description logics then determines what you can express in this logic and also how complex the reasoning problems are. Right? So for example, in EL, the language we are going to look at next, we have top, we have conjunction, and we have existential restriction, but we don't have negation. Right? And if we don't have negation, that means we don't get disjunction through the back door, if you will. Right? And also we don't have disjunction as a primitive. So this really is a simple language, and we will see that it offers to decide reasoning problems with indeterministic polynomial time. And the good news is we can even add standpoint modalities to this, keeping this nice complexity. Right? For other languages, reasoning is more involved. Right? So for ALC, for example, where you have the full Boolean connectives and existential and universal restriction. But for example, no number restrictions. Their reasoning is harder. Right? So you have to go beyond polynomial time, which is clear because you already have the full Boolean logic in there. So when I speak about reasoning, for description logics, there are a number of standard reasoning tasks. Right? So for the interpretations and modelhood I have just introduced, it's clear, or it's natural to define that a subsumption is satisfied by a description logic interpretation if it is the case that everything that's a C is also a D, and an assertion is satisfied if it is indeed the case that, right, so the assertion says A is a C, right, and this holds if indeed the interpretation of A is contained in the interpretation of C. Right? And then, as usual, our notion of logical entailment says a statement, which can be an assertion or a GCI, a statement is entailed or logically follows from a knowledge base, so from a T-box and A-box, so that should actually be a T-box and A-box, if for every interpretation that satisfies both the T-box and the A-box, we find that the interpretation also satisfies this statement. And now, given such a knowledge base, then the typical reasoning tasks that we want to deal with, because they arise in practice, are asking whether it follows from the knowledge base that C is subsumed by D. Right? So is it really the case that every primary forest is a forest, for example? We also want to know satisfiability. So that's basically one of the first tasks we have to solve as knowledge engineers when we start modeling a new domain. Right? So writing down GCIs about our domain, defining concepts, then one of the first things we want to do is does it actually make sense? So is there one way to interpret all of our axioms that works, that satisfies all of the axioms? And then we also want to know for concrete things, right? So is this particular piece of land, can this be considered to be a forest? Right? Or some specific kind of forest in this example. Right? Typically, this again depends on the concrete description logics, but typically these problems can be reduced to each other, which is good news for us as computer scientists, because then this means it suffices for us to implement one of them and then just still be able to decide the others via reductions, right? That we can implement on top of reasoning algorithms that we already have. Right? So typically, when reducing subsumption to satisfiability, for example, we would check whether there's an interpretation of our T-box where some individual is a C but not a D. Right? And things like that typically can be done in most of the cases. Right? There are some exceptions where you lack the expressive means to really do these reductions, but typically it works. So here's an example that you've seen before. So Tim has shown this to you. This is something that we want to do in description logics. Right? So we have our T-box defining what a forest is and a forest ecosystem. And then we have an A-box speaking about concrete instances of these concepts. Right? So this says E is a forest ecosystem, and this forest ecosystem is in a binary relation, so it has a role, has land, to this piece of land L, and this piece of land L has an area of at least half a hectare. Right? And then from T-box and A-box, we can conclude one of these queries. Right? So this E is also a forest, right? Because it satisfies this forest ecosystem by statement, but also it has a piece of land, right, whose area is at least 0.5 hectares. Right? And the other query wouldn't be entailed. So, as I said, there are many different description logics. So that's why people always talk about description logics as a so-called family of knowledge representation formalisms, because they are related with each other, right? So by adding one piece of or one constructor to the language, you can move to the next language, which sometimes gives you no additional expressiveness, sometimes increases complexity, but people have been studying this for decades now, and this is mostly well understood. So we can basically use this more or less off the shelf. So the first description logics we want to look at is EL, and in this case EL+. So the original EL language only had top and conjunction and existential restriction. The plus refers to people later on adding stuff to this language that they observed can be added without violating this polynomial time reasoning complexity. And among those things were role inclusions, and in particular complex role inclusions, right? So where you can build role chains on the left and then say this is included in some other role name. And even though it is relatively inexpressive, it still is being used for some large-scale medical ontologies, for example, the SNOMED clinical terms, and also the gene ontology can be, in large parts, expressed within EL. But also the National Cancer Institute's thesaurus also works within EL. Then, as one of the main and also historically important description logics, we have ALC, which basically has everything that EL has, plus negation, and therefore using De Morgan's laws, also disjunction, and using the duality of existential and universal restriction. By having negation, we also have universal restriction implicitly. And this already gives you a complexity jump to P space for satisfiability. But this is one of the, as I said, historically important description logics. And the naming here, so that EL stands for existential language, right? Because you have this existential restriction. ALC stands for attributive language with complement. So the complement refers to this negation here. Right? And then there are further languages. One of those we will also consider, so it's called SHIC. And here people started, right? So if you continue this ALC and then you add, so people started adding ever further letters to the description logic names and got ever longer names, right? So you would, for example, add qualified number restrictions to ALC, then you would have ALCQ, and so on. So people at times tried to shorten the names, and so they said, well, if we take ALC and transitive roles, right, then let's call this S, right, and to get shorter names. Right? And then starting from this S, people also added role hierarchies, right? So this is simple role inclusions where you don't build role chains on the left. So you have role hierarchies, that's the H. Then you have inverse roles where you can swap the direction the role goes, that's the I, and then you have the Q for the qualified number restrictions. And if you do this, there's another potential increase in complexity, but this is a useful and expressive language underpinning the web ontology language description logic profile. And now, this is all so far without standpoints, and our goal, as I said, is allow us standpoints within these languages and then checking how and when this changes complexity of the reasoning problems, right? And I wrote here, this sometimes comes at no extra computational cost, and our job as researchers is exactly to figure out these sometimes, right? And I will report on some of the cases where this worked, where we could also map out the boundaries, right? So find constructors, such as I, H, or whatever, where if we added this additionally, we would lose the nice computational properties. Questions? Okay, then let's move forward and let's have a look at standpoint EL. So as I said, this is one of the less expressive, one of the simpler description logics, but still the useful thing there is that we can add standpoint modalities, and this is one of the nice cases where we don't increase reasoning complexity. So as I already said, this is used for the for example, for the systemized nomenclature of medicine, so SNOMED, the clinical terms, also the gene ontology and others, reasoning in EL is P-complete. And what we could show is the tractability is preserved when adding these standpoint modalities. Right? This is not completely straightforward. And also there are some extensions of EL. That's why we only have this EL+. In the literature, you will also find EL++, where people added a thing called nominals, where you can, within the terminological, within the T-books, refer to concrete individuals. And once you have this, original EL stays within P. However, the standpoint version goes to XTime. Right? So adding standpoint modalities is not always complexity neutral. We really have to look at the details. So, but one of the other important things here is when adding standpoint modalities, we will be using the monodic fragment. So we can essentially apply standpoint modalities to within concept terms. Right? Not only at the level of axioms, but within concept terms. And so we can express these bridge axioms that we want to express. So in our running example, that would be the different perspectives that the land use ontology has on forests versus the land cover ontology on forests. Right? So this only uses two different views on forests. So in her PhD thesis, Lucia has found a work looking at hundreds of different definitions of forests. Right? So this is a real issue. We are only using this example as a small toy example to exemplify or to show what standpoint logic can be useful for. Right? So as we had it before, things we want to express and can now express within standpoint EL, as I will show you. So what are unequivocally our primary forests according to the land cover standpoint are conceivably ecosystems according to the land use perspective. Right? So things like that we want to express and will be able to express within standpoint EL+. So that's the formal syntax. So we can build concept terms, so complex concepts as usual. So in addition to the description logic vocabulary consisting of concept names, role names, and individual names, we additionally now have a set of standpoint names, right, that we add to the vocabulary of the description logics, obtaining a standpoint description logic. And these standpoint names are used for the standpoints, right? And as usual, we include this star, this universal standpoint, referring to the set of all precisifications. So once we have one of these standpoints, we can use the modalities. And the important bit here is, because we are in the monodic fragment, that we are allowed to use these modalities within concept terms. So in order to build a concept term, you can either do a concept name, you can do the top concept, you can do conjunction, existential restriction. Then we additionally have this self concept. So that's a special name, essentially saying that an individual satisfying this has an R relation with itself. Right? So this is meant to express reflexive arcs in your model, which can sometimes be useful and which we could add for free in terms of complexity. So we just added it. And most importantly, what you can do once you have a complex concept, you can put a standpoint modality in front of it. And that can be a box or a diamond. And here we really have to introduce both because we don't have negation. And this means we cannot express one in terms of the other. Right? So typically, when you have negation, you can it suffices to allow one in your syntax because you can express the diamond as not box not. Here we don't have negation, so we have to allow both. This is fine. It's only sometimes annoying in proofs because you have to consider one more case. Right? But we will see that actually the diamonds also will lead to the most complex treatments in proofs typically, right? Because the diamonds require some things to really be there, and you have to find witnesses for them and always deal with these witnesses. And this can sometimes be technically challenging. Okay, so we have this language for concepts, and once we have concepts, we can use them as usual. So we can build general concept inclusions, and we can build complex role inclusions. So we can do role chains, and in particular, this means we can get, for example, transitive roles through the back door. Right? So this is one way of doing this. We don't have inverse roles, for example. And in our A box, we will still have assertions, so where we can talk about concrete concepts and role assertions. We even have the possibility of adding standpoint modalities to these assertions. Right? And we can even build conjunctions of such assertions. And we can even sometimes negate them. So here we allow even more. So once we have an axiom, we allow to negate it in a controlled form. And we will see that this doesn't really affect the complexity. We also have sharpening statements. So previously, what you have seen as sharpening statements was always of the form S is sharper than T, for example. Here, we have a more general form where we allow to intersect intersect standpoint names. So you still have the sharpening statements you had before, right? By just setting n to 1, just write one standpoint name here. But you can also express more general things. Right? And of course, this bears similarity to these role chains. Right? So this is also something that we could do in a complexity neutral way, so we decided to allow it. So that's our language. And here you can see some examples in this language. Right? So here, for example, we can now express the bridge axiom that I mentioned earlier. So here I can say, what is unequivocally a primary forest according to the land cover perspective is conceivably an ecosystem according to the land use perspective. Right? So that's something that I can now express by a simple axiom in standpoint EL+. Right? I can also say if something is conceivably a forest according to the land use perspective and unequivocally a land area according to the land cover perspective, then it's a piece of land. Right? And I can take these axioms, right, potentially negate them. Then I have a literal, and I can take conjunctions of such literals and can again put standpoint modalities around them from the outside. Right? And I can also do this to A-box assertions. Right? And so this gives me a pretty expressive language with which to express things about my application domain. Right? So in particular, I can also say that certain GCIs are not satisfied, right? Which is also something that didn't really exist in standard EL. So that's the syntax. So I can say a lot, but of course I also have to define what it means. And for this, we are using so-called description logic standpoint structures. Or sometimes we also reverse the name and call it a standpoint description logic structure. So the point is that we now have a many-dimensional, or more specifically a two-dimensional structure. right? So we have one dimension for the standpoint names, where we have the precisifications. And we have another dimension where we have these individuals, right, that exist in all of the precisifications, but that might have different properties in different precisifications. Right? And this is reflected in this formal definition of such a structure. So we have a four-tuple. We have this delta, so that's the non-empty domain. That's going to be the interpretation domain shared by all the interpretations of all the precisifications. So they have a shared domain, and this makes life much, technically much easier for us. Right? There's also the possibility of saying, well, we have our different precisifications, and all of them have a different domain, but this can be modeled within the setting of the shared domain, because you can take the union of all of those as the shared domain. And then sometimes have to take care of whether this thing exists in your world or not. But we opted for the technically nicer variant where we have a shared domain. Right? So that's the idea. As usual, pi is the set of precisifications. Right? So those will lead to the different standpoint extensions. As usual, also, we have the sigma function mapping each standpoint name to some non-empty set of precisifications with the extension of the universal standpoint of the star fixed to the set of all precisifications. And now the important bit is this gamma. So previously, we had a function mapping each precisification to a propositional valuation, right? And here, since we have a description logic domain, if you will, what this gamma does is it maps each precisification to a description logic interpretation, with all of these interpretations sharing the same domain that is already given by this overall standpoint structure. And we additionally require that individual names, so those from Ni, are interpreted rigidly. That means they are interpreted as the same individuals across precisifications. This also makes things technically easier for us. And then the interpretation of the standpoint or of the typical description logic constructors is as usual. Right? So conjunction is interpreted as intersection of concept extensions and so on. So we only have to give the remaining definitions. Right? And so, in particular, what we have to give is how we interpret standpoint modalities occurring within concept descriptions. Right? And here, essentially what we say is the extension or the interpretation of this diamond as C, right, where diamond as C intuitively expresses all the things that, according to S, could conceivably be a C. Right? We formally interpret it as the extension of C's across all pi prime that belong to the standpoint S. Right? So here we take the union. We want to have everything that is a C somewhere, right, in some pi prime. And dually, for box as C, right, so those are the things that are unequivocally C's across S. And so what we do here is we take the intersection. Right? So we intersect over all precisifications pi prime that belong to S. And we intersect the extent of C in these precisifications. So we take all individuals that are C's everywhere across the standpoint S. Right? So that's the idea. And as I said, the self thing is something that existed before, so we didn't invent it. It's relatively cheap and easy, and here you just take all the delta, so all the individuals that have an R relation with themselves. Right? This reflexive arcs. The other constructors are standard description logic EL, and for the conjunctions of literals, we use standard interpretation of conjunction and negation. Right? So there are no surprises there. So once you have a box on such a formula, so a conjunction of literals, then of course the box is interpreted as usual, right? So the formula behind it should be true in all S precisifications. If it's a diamond, the formula should be true in at least one S precisification. And for these extended sharpening statements, we basically take the intersection of all of these extensions, right? And then we check whether they are a subset of this sigma of S. And here we even allow, also on the left-hand side, but there it doesn't make much sense, but also on the right-hand side, we allow a special symbol representing the empty set. So what we can even express here is standpoint disjointness, right? We can say S and T must not have any precisification in common. That's something that we can additionally express here, which we could only express through the backdoor, if you will, before. So if we only consider the sentential fragment, right? So to recap, what we could do there is use our standpoint modalities in front of full axioms. So for example, full GCIs. Right? We wouldn't be able to express bridge axioms. Fortunately, by moving to the monodic fragment, we are now allowed to apply the standpoint modalities on the level of complex concepts. And this allows us to express bridge axioms, like the one we've seen before. And the nice thing is that this doesn't affect complexity. Right? And this is not, as I said, this doesn't always come for free. And in this particular case, also it didn't. So we tried for quite a while how to show. So we had the suspicion that it works, but it was far from trivial to show this. So I want to give you some idea on the technicalities that are necessary to show that you can actually allow this and still keep the same complexity. So this is good news, but it's not automatic. So what we did was we proposed a deduction calculus, so another type of proof system, where we could establish logical consequences of a given EL or standpoint EL knowledge base. Right? So the idea is that we have these completion rules that basically look at a knowledge base and check whether there is some one-step logical consequence that we could add to the knowledge base, right, which is semantically valid, but which is not explicitly there. Right? So the idea is to, within limits, add all logical consequences to the knowledge base, and then check whether this either contains the subsumption we are interested in, or whether it contains some impossibility, which would then indicate that our knowledge base was unsatisfiable from the start. Right? So that's the idea. In order to make this work, we first had to devise a form of normalization, which was a quite technical task in itself, because basically you have to pull out the modalities, right? So according to the syntax, you can nest these modalities as you wish, right? You can nest modalities, interleave them with existential restriction and conjunction. So one of the more involved tasks was to devise a normalization procedure for this, and then show that it actually doesn't blow up, right? Because we want to keep PTime reasoning, so we have to make sure it only induces a polynomial blow up, if at all. And it also, of course, should be equivalence preserving within limits. But all of this worked, and in the end, we could give a specific deduction calculus. So this is not the full calculus. The full calculus would span over several slides. So this is only a selection of the rules. One additional thing is that we had to even introduce a new connective, if you will, as a shorthand because it was being used so many times. Right? So we have this arrow occurring on the right-hand side of GCIs, and this basically expresses that in the context of A, you have something that subsumes A, and intersecting this with B, then is subsumed in turn by C. Right? You have to don't fully understand this. It's only for showing you that we have this additional thing, and we are later on also going to use it. Okay. But before I go into details regarding these rules, later on I also have an example derivation using these rules. Let's have a quick break, and then maybe let's reconvene at 10:05. So. Welcome back, and let's continue. So we have these. We have this calculus with its completion rules, and as I said, the idea is to complete a given knowledge base in the sense of adding all logical consequences, right? But of course, we don't want to add trivial consequences like C is subsumed by C, right? And C is subsumed by C, and so on. So we have to take care not to derive too many things. Right? But besides that, it was still challenging to devise this calculus. As I said, this is not everything. These are only a few rules. But I still want to show you some of them to give you an idea on how this looks like and how later on this can be used on an example. Right? So here we have one rule, C1, that basically says if in the context of T, B is subsumed by C, and then additionally in the context of SC is subsumed by D, and you have a similar thing stating that in the same context of B, D is subsumed by E, then, right, and now if you only look at these here, you get basically the transitivity idea of this rule, then in the same context with the same standpoints, C is subsumed by E. Right? So that's the idea of this rule. Then you have rules on sharpening statements saying that if S is both sharper than S1 and S2, and the intersection of S1 and S2 is sharper than S prime, then of course S is sharper than S prime. Right? Stuff like this. Then you have rules for enforcing these sharpenings. Right? So you can say that if it's unequivocally the case with respect to S prime that psi holds, and S is sharper than S prime, then of course also in the context of S, this same psi holds. Right? So this is pushing down or pushing the boxed formulas along the standpoint hierarchy, if you will. Then we also have other rules. So here, for example, so this is similar to C1. Here you have that top is subsumed by D, right? So basically this says that C is subsumed by D, and D is subsumed by diamond SE, then of course also C is subsumed by diamond SE. Right? So that's the idea here. And here we have one rule for moving bottom around. So here we say C is subsumed by box S, and this then says top is subsumed by bottom. Right? And this is something that is obviously a contradiction. Right? So bottom is the concept name to be interpreted as the empty set. So nothing satisfies this bottom concept. So what this basically says is that everywhere in the context of T, C must be empty, right? So there can be nothing that is a C, for otherwise top would be subsumed by bottom, right? So this is the logical consequence that's going on here. Right? Now we have these rules, and the idea is that we can use them for concrete reasoning, and I want to show you one example how this can be done. So here we have a small example, ontology from the land use and land cover domain. So we have the statement saying that according to the land use perspective, what is a primary forest is unequivocally, according to the land cover perspective, also a forest. Right? So this is similar to the bridge axiom we had before, only that we now have a box instead of a diamond. We also have that if something is a primary forest, then in the additional context of the land cover ontology, then every forest is also a land area. And then if something is a land area, it is conceivably a fertile area. And here we have the standpoint of the Food and Agricultural Organization fully subscribing to the views of the land use ontology. Right? So the Food and Agricultural Organization might make additional semantic commitments in how they use their vocabulary, but they agree in how they use it. They agree in all the commitments that the land use ontology makes in the use of the logical vocabulary. Now assume we are interested in whether, according to the Food and Agricultural Organization, it holds that this subsumption is the case, so that every primary forest is conceivably a fertile area, right? Conceivably according to the land use perspective. And then we can derive this using our rules on the given axioms of our ontology. Right? And here we use C1. So C1 was the one with transitivity of subsumptions. Right? And so here we have, as you can see, the same prefix. And here we say anything is a forest. And if it's a forest, then it's also a land area. And therefore, anything is a land area. Right? So that's just applying C1 on these first two axioms. Now, we have this. We also have rule 3 stating that a land area is subsumed by conceivably being a fertile area. And so basically we can replace this by this conclusion that it's conceivably a fertile area, right? So that was rule F2, saying that if we have a D here, and D is subsumed by diamond SE, then we can replace this whole thing by diamond SE. Right? And this is what we do here. We replace this whole thing, which is subsumed by diamond LU fertile area here. Right? And then finally, we use this sharpening axiom saying if one standpoint is sharper than the other, then everything that unequivocally holds in the more general standpoint also holds in the more special standpoint. Right? And so we can conclude this also for the Food and Agricultural Organization. So that's the idea. And so we get a yes as an answer to our query. Right? Of course, this calculus is not intended to be used by humans. Right? So this is only an example to show you how it would work. In principle, calculus is much too large and to actually do this by hand. So we provided an implementation in Datalog. And this is also how we showed that this actually is possible to implement in deterministic polynomial time. So first of all, we of course have to show soundness and completeness. And in this case, it's refutation completeness. So soundness means well, whatever the algorithm or whatever the completion rules derive is actually a logical consequence of any knowledge base given to it. Right? And refutation completeness in this case means that whenever the knowledge base is unsatisfiable, then we will derive an explicit contradiction with our algorithm. And this is shown in the contrapositive way, if you will. So we show if the algorithm ends up with a knowledge base where no further rules are applicable, so which is saturated, but it is also consistent in the sense of there being no obvious contradiction contained within the knowledge base, then we can use the information we have in the saturated set and the fact that it is saturated, right, to build one interpretation that satisfies all the axioms, so all the assertions inside the knowledge base. And so the idea there is we use the information that none of the rules is applicable, and we have no obvious contradiction to construct this canonical model. So this is not necessarily easy to construct, but it can be done. So that shows soundness and completeness. Right? We still have to show a termination. And this relates to my earlier saying that we want to make sure we get all the logical consequences except for the infinitely many trivial ones. Right? So we still have to watch out to make sure this whole thing actually terminates. And the way we did this was we encoded the calculus as a Datalog program. So this is a form of logic programming without function symbols. And for this, there exist dedicated reasoners that do this in polynomial time. So in general, so if you've seen this before, in general, Datalog evaluation is X-time complete, but this only if you allow for an unbounded arity of predicates. Right? So the exponentiality comes through ground instantiation if you allow the arity of predicates to increase. In our case, the calculus only uses a fixed number of predicates, and they have a maximal arity. Right? So the maximal arity is 5, if I'm not mistaken, or 6. In any case, it's bounded. And in this case, Datalog evaluation for a fixed Datalog program with known maximum arity of predicates, in this case, it becomes deterministic polynomial time. Right? So the implementation we have is still not something that you might want to use in practice for very large ontologies, but at least it works in principle, and it gives us this PTime complexity result. And also the important point here is that we have an implementation of the calculus where the arity of the predicates is independent of the T-box and the A-box. Right? So T-box and A-box are later on added via Datalog facts using the existing predicates that we use in any case. Right? So this, other than the size of the ontology, in practice, the T-box and the A-box, in theory, do not increase or affect the complexity of reasoning in any way. So here is one excerpt from how we encoded this calculus in Datalog. So basically we used Datalog predicates for the different forms, different syntactic forms of axioms that are still allowed in the normal form, right? So you can have a conjunction on the left, for example. So this basically represents that you have a GCI with conjunction on the left. So you have box S, C, and D is subsumed by E. Right? So this is what this expresses. Then you have an existential restriction on the right. So box S, C is subsumed by exists in R, D and so on, right? You have a diamond on the right, so box SC is subsumed by diamond S prime D, and so on. Sharpening statements, and so on, right? And so using these predicates, we can then turn our deduction rules into Datalog rules, right? So this is the transitivity rule we have seen, right? So if D is subsumed by E, C is subsumed by D, then in the same context, C is also subsumed by E, right? So these Datalog rules are read from right to left. So body implies head, right? So this is how we then apply these deduction rules, right? So transitivity of sharpening statements, right? So if S is sharper than T and T is sharper than U, then S is sharper than U, and so on. So we have a proof of concept implementation of this, a prototype based on the Datalog reasoner souffle. We used souffle because it offered, so back at the time, a couple of years ago, it offered nice software engineering things, such as static typing, algebraic data types, which are very useful if you have these many complex rules, complex data types. It might be the case that with another reasoner, for example, the NeMo reasoner, it will run faster, but we haven't tried that yet. So this is certainly one potential aspect of future work. So to wrap up this standpoint EL plus section, we offered the explicit syntax of standpoint EL plus. So we have standpoint modalities, and they are allowed as first class EL plus constructors, and in particular they are allowed within concept terms, meaning we are within the monodic fragment of EL. Right? We have in the semantics these standpoint description logic structures. They share an interpretation domain, and at each precisifications, concepts can be interpreted differently. Here we have seen that allowing standpoint modalities within concept descriptions essentially leads us into the monodic fragment, but this time this gives us no issues because we have managed to show that the complexity does not increase. Right? But in general, this is not always the case, as I said. And in order to show that this actually works and that the reasoning problems can be decided efficiently, we provided this calculus and we implemented it via the Datalog language, which can also be implementation, which we did in a proof of concept manner via standard Datalog engines. Okay, questions to standpoint EL plus. Okay, then let's maybe start looking at some more expressive standpoint logics. So we have seen EL, but we have also seen before that there are more general and more expressive description logics. Right? And what EL is certainly lacking is negation, which can sometimes be very useful, disjunction. So for expressing different options or unions of concepts. We also don't have universal restrictions. So what Lucia and Sebastian looked at next was the description logic chic, which not only has these things. So as soon as you add negation, basically to EL, you have the full ALC language due to duality of conjunction, disjunction, and existential and universal restriction. So they looked at an even more general language. So as I said, if you extend ALC with transitive roles, you get the new name S, and then you add role hierarchies. So these simple role inclusions, inverse roles, and qualified number restrictions, right? So that were the at least NR successors that are C. Then you get the description logic chic. And for this, So this is the formal basis of the web ontology language description logic profile. However, the added means of expressiveness also come at a price. So this is no longer, reasoning is no longer within PTime. It is PTime complete in this case. But still, there's a valid question to be asked, namely, can we also look at the monodic fragment of Schick? So can we add standpoint modalities on the concept level without increasing complexity? And Lucia and Sebastian showed 2 years ago that yes, this is possible. And I want to briefly show how this works. So this is plain Schick. So as before, we have top and bottom, we have concept names, we have conjunction, disjunction, we have existential and universal restriction. We have qualified number restrictions, so at least n are prime successors that are C's, or at most n and at least n. And finally, and this is the new thing, we have the standpoint modalities in front of concept names. So here we just use this the circled dot as a placeholder for the two modalities. This Schick has a quirk because it makes a distinction between so-called simple and non-simple role names, and this is a purely technical issue. So the point is that within qualified number restrictions, you are only allowed to use so-called simple role names. And simple means they are not allowed to be transitive or more generally have any transitive subrole. And the restriction is necessary because otherwise, if you allow transitive roles here, you get bad interactions between counting and transitivity, and this breaks decidability. Right? So this is a necessary restriction to actually keep this logic decidable, but nothing that is of major interest to us. I just wanted to explain what this simple here means. We have the same kinds of axioms. So you have GCIs, transitivity assertions, and role inclusions. Right? But simple role inclusions only, no role chaining. And then again, we can build formulas. Right? So we can have a conjunction of axioms and possibly negated axioms. And we can put another standpoint modality in front of them. Sharpening statements are, again, of this more general form. In order to do reasoning with them, you have to obtain a normal form of these standpoint Schick axioms. And the interpretations are as before. So again, we have structures with a shared description logic interpretation domain with a set of precisifications. This sigma assigning each standpoint name a set of precisifications, and this gamma assigning to each precisification one description logic interpretation over this same domain delta. Right? And as before, diamonds in front of concept names are interpreted by union. Right? So you take all the individuals that are a C in some S precisification. Here you take the intersection, you take all the individuals that are C's in every S precisification. And then likewise, for the at most n R successors which are a C, you again count the number of R successors of this delta that are C's, right? And if there are at most n such successors, then you take this D into the extension of that complex concept, the delta. And as usual, if you have these conjunctions of literals and you put a box in front of them, then this means the conjunction should hold in each and every precisification belonging to that standpoint. And now, and this is basically a preview for what we are going to start with tomorrow, this standpoint chic language also has a small model property. However, this is slightly different from the small model property you have seen for the sentential fragment of first-order standpoint logic. Right? So in the sentential fragment, the idea is to only keep witnesses for diamonds, so for unsatisfied boxes, belonging to the original formula. And this works because we only have this true-false status in the sentential fragment. Here we have a monodic fragment, and so things are slightly different, and we will see that we will end up with polynomially many precisifications. Things are more involved, but fortunately, it still works. More on this tomorrow. So until then, thanks for your attention today, and see you tomorrow.